Okay, so today we have 2 pages of homework to go through. And well, the first page is pretty straightforward. The second page, I'll have to explain something about the limit definition for integrals, and we'll see some estimation notation as well. But yeah, so 7 and 8, hopefully you're able to do them on your own just fine. So the idea for 7 is all we have to do is draw the functions or draw what the integral represents, and then with that you should be able to use geometry in order to figure out how to represent this integral as an area. So we start off at trying to draw 2 minus x. We end up needing to extend this 3 to the left, so that's going to bring you up to 5. So you'll be like up here. And then you have to go 5 to the right. So first, you're going to hit the x-axis at 2, and then you're going to go 3 more to the right. So you go to -3, which lands you there. And so you can see that when you draw this, they end up forming 2 triangles. And so this integral is just calculating the area of these 2 triangles. So the triangle on the left, well, it has a height of 5 and a base length of 5. The triangle on the right has a width of 3 and -3. So calculating the area, you're going to end up with 25/2 minus 9/2, which ends up being 16/2, which ends up being 8. For part B, well, I usually have to explain this. So this, when you see this function, you should get used to recognizing that this is the upper half of the circle. The way that you see that this is actually representing a circle is by setting this function equal to y and squaring. So when you square both sides of this equation, you end up with y squared is equal to 1 minus x squared. And then moving things over, you get x squared plus y squared is equal to 1. And that certainly should look familiar. That you should immediately recognize that is the equation of a unit circle. And so all we need to do is, if we were to draw like what this problem is actually asking us to find, well, it's asking us to find the area of half of a circle. So that's 1/2 pi times r squared, but r in this case is 1. So the area we end up getting is pi/2. Okay. Any questions so far? Okay. Right. So number 8. Well, the important part of this problem is actually the fact that we're told f is increasing. Okay, so we're told f is increasing, and then we want to compare the L5 with the integral with the R5. That's what this is asking us to do. Let's draw a picture of a function that is always increasing. Okay. And well, it's going from 0 to 10. That's fine. We can just say that that's what this is actually doing, 0 to 10. So now consider what happens to a subinterval. Well, so let this be the subinterval. So the integral, it would calculate this area exactly. The left endpoint approximation would calculate the area of the rectangle with the height in blue. And the right endpoint would calculate the area of the rectangle whose height is in red. Okay. So you can see that the blue approximation is going to be an underestimate, whereas the red one will be an overestimate. And that's all you need to know to set up this the set of inequalities. So that's telling you that L5 is going to be less than the integral, which is going to be less than R5. And this all is because of the fact that this is an increasing function. If it were decreasing, then you'd actually have this in reverse. You'd have R5 is less than the integral. So yeah. Does this make sense? Any questions? No questions. Okay. So number 9. We've done things that are like this, except in this case, it gives the information to us in a table form. So we want to do left endpoint approximation. What we need to see is which values do we actually take for the left endpoint approximation. So hopefully, like you understand that because for each interval you end up taking the left endpoint, that means that you end up using the values from 2 to 8. This is what the left endpoint uses. And I'll contrast this with what the right endpoint would use. It would use the values from 2 to 10. It would exclude the value 0. So let's go ahead and calculate this total distance. So the idea is we need to integrate this velocity function, and we would approximate this using rectangles. And here in this problem, the rectangle's width is 2 because the time step is 2. And then the heights are given by the v of t. So we end up using all of those values except for the last one. 10 plus 14 plus 16 plus 18. And then if you calculate that, you'll get 2 times 58, which ends up being 116 feet. Okay. Right. So now 10 and 11. So these two problems are kind of introducing you or checking that you understand sigma notation. So I think sigma notation is pretty straightforward. I don't know. If you're confused about it, you can ask me. But so this problem, the number 10 is asking us to sum integers, the values from 5 to 1003. And the easiest way to do that is to just make the summation do exactly as it's said. So we're just going to sum the values I as I runs from 5 to 1003. And this represents the sum that you would have to compute normally. Yeah. You're not transforming the function at all, so it's very easy. For 11, it wants us to actually compute this guy. So notice that this only has 5 terms, so it's pretty reasonable to just compute this by hand. The one thing that you could do before you compute, so one way you could do this is just by expanding that out into what the actual terms are at this stage. So you have like 2 up to 10 here that you'd be adding. But what we can do is we can actually introduce one little algebraic step, which is we can actually pull the 2 out. Because that 2 is being multiplied by every single term in the sum. We can just pull the 2 out. It's basically just factoring, reverse distributing. So that becomes this sum now, which then we can expand that out. That's 1 plus 2 plus 3 plus 4 plus 5, which is going to be, I think, 15. And so then the overall answer you get is 30. Okay, so any questions on sigma notation? No. Okay. Right. Well, then the last two, well, they involve this limit definition of integral. So the first one wants us to write this integral as a limit. The second one basically wants us to do reverse. We have the integral written as a limit, and we want to find the integral. Right. So let's kind of talk through how this construction works. So say that we have an integral from a to b, f of x dx. And pictorially, that's something that looks like this, from a to b. And you would subdivide, and you have like these rectangles. Okay, so if you think through how these approximation methods work, the left-hand point and the right-hand point, you see that there's a dependency on the number of subdivisions that you perform. And the idea is that as you make the number of subdivisions go to infinity, then the rectangles get smaller and smaller, and the approximations get closer and closer to the actual area you would compute, the integral that you compute. So the idea is we let the number of subdivisions, which I'm denoting by capital N, let that number go to infinity. And then you're summing up the areas of all the rectangles. So that tells you that you need a sum. And the easiest way of indexing is to say, let I go from 1 to n. So I is like each individual rectangle. So what remains now is constructing a formula for the height of the rectangle and something for the width of the rectangle. Now, the width of the rectangle is the easy part. Okay, so if our integral is going from a to b, then the length of the integral is b minus a, and the subdivisions are going to divide this length into n even pieces. So this this would denote the width of each rectangle, and commonly you'll see this written as delta x, capital delta, which is a triangle shaped thing. So this is the width of the rectangle. Now the height is a little bit more involved. So for that, I would draw the x-axis, but in a little bit more detail. So now that we know what the width of the rectangle is, we can kind of relabel the x-axis. So we have a plus delta x for the first. Then for the second, we'd have a plus 2 delta x. And then you can see the pattern. So it's going to keep going until you finally end up at b. Okay, so what happens is that each of these values, we would call this an xi. So the way that it works is you'd have a plus I times the delta x. So you start off with a0, and then you go up to a well, technically an, but an would end up being b. Right. The point of this is for every rectangle, you end up picking a value within the subinterval. And so you can pick any particular value. It's easiest if we just pick, I don't know which endpoint it is, actually. I'm noticing there's a slight discrepancy, but well, the way that I'm writing the summation, it ends up being the right endpoint approximation, I think. So let's just combine these two notations down. So this delta x is the width of the rectangle. This f of xi is the height of the rectangle. Right? The xi is the thing you're feeding into f, which will then give you back a height. Yeah, so in this format, with I going from 1 to n, the first term that get is going to be a plus delta x, which is this guy. So this is going to be technically right endpoint approximation. But then because you let n go to infinity, both of those approximations should converge down to the area of the integral. If you wanted the left endpoint, you would say this I goes from 0 to n minus 1. Okay. So now let's go ahead and use this notation. So we re-express this limit, or this integral as a limit. So n goes to infinity, summation I equals 1 up to n. Our f is this sine of x squared. The one thing I'm going to need to do is figure out what is this xi, the delta x as well. So notice that the integral is going from 0 to 5, so its length is 5. And so we end up having that the delta x is 5 over n. And the xi, well, we start off at 0. Well, I'll just write it symbolically first, and then I'll plug it in. So it would be 0 plus I delta x. But that simplifies. So this simplifies to 5I over n. Okay. Well, let me just make that look like an I. All right. So we're plugging xi into the function 5I over n, and we're squaring it. Since the function is sine of x squared. Then delta x is 5 over n. And so there we go. We've converted this integral into a limit. All right. So now 13 is asking us to do the reverse. Well, so there's actually two different ways we can interpret this. And the end result that we end up getting is going to depend on how we interpret it. So the first thing we could do is we could consider this to be our xi. And the second thing would be to consider 2 plus the I over n as being the xi. I'll go through what that happens if you do that. So, but if we consider xi to be just this portion here, then that's telling us that the function that we're looking at ends up being 2 plus x squared. And this 1 over n is supposed to represent the delta x. So that tells me that this 1 is actually indicating the length of the thing you're integrating over. Okay. So the length that you integrate over is length 1. And this xi, well, xi is denoted by a plus I delta x, right? So whatever the a value is, that's where the length of the integral starts at. In the way that I've indicated here, the a is 0. So you start at 0, you go a length of 1. So that tells you that the integral you would construct starts at 0 and goes to 1. And then we can just plug in the rest of the things. So 2 plus x squared dx. All right. So that is one way to interpret this thing. Okay. The other way is, I'm going to use a different color. The other way is, what if you let the whole thing, 2 plus I over n, let that be your xi. Well, in that case, your function ends up being x squared, just x squared. And again, because of this 1, the length you integrate over is still length 1. But interpreting what the xi is, again, it's a plus I delta x. This is the I delta x. This is the a. So 2 ends up being a, which means that it starts at 2 and it travels length 1. So the integral you can calculating is the integral from 2 to 3 x squared dx. So either of these two integrals, you can pick which one you prefer. But yeah, either of these two is a way to represent this limit of this sum. And it's kind of curious that you can do that. In fact, this is kind of hinting at something that you learn about later called U substitution. So it turns out that you can actually go from one integral to the other by performing a u substitution, letting u be x plus 2, or I guess you could probably go in the reverse way as well, but it's a bit more contrived that way. Okay. Well, that's all I really wanted to say. Are there any questions?
I had a question on 8.
Yeah, sure.
So with this one, is there any way, I'm trying to see how to word this. Is there any way you could find how much greater your right endpoint would be than from like your left endpoint?
Much greater. Mm,
Or
I'm pretty.
would you have to show it like that basically?
I think without additional information, this is as close as you can get. Like, what you're trying to say. I mean, you're definitely asking something interesting. Um, it's just that in order to know, like, I guess you're basically asking about how much error there is, or you're trying to calculate. It sounded like you're trying to calculate this quantity.
Yeah.
So yeah, the thing is, that's really going to depend on the function, I would say. Because if the function is growing very quickly, or if it like imagine that it has a very steep slope, that aligns perfectly with the number of subdivisions, then in that case you have a very large error. Versus if the function is not changing too much in the subdivisions. So really, it's going to depend on the function, the behavior of the function. So without additional information, I couldn't conclude that much, I would say.
Okay. That's all I had. Thanks.
Are you doing like some other sets of problems that are using this?
I'm not.
Hmm. Okay. All right. Um, any other questions? No, no other questions? Okay. Well, then I'm gonna stop